really something super small. And I can tell from his eyes he was really into this. And he said, is there a possibility I can be part of your research? And remember back then, he was a sophomore. Most of the sophomores or freshman students are really struggling with calculus or physics. So I can really tell that he's different. He has motivation to do more. So that possibility came true 3 summers ago, when he won one of the department summer research assistantships. So we immediately got into this project, which was really to use some chemistry, physics tricks to make these nanopores. So after summer, he took a break from the project because he wanted to also get a math degree. So he's returning this semester, continuing work, and I think that his plan is to take a little break from here and then eventually get an advanced degree in mathematics. So let's give a warm welcome to Adam.
So I'm Adam Smithson, working with Dr. Shi on fabrication and characterization of aluminum nanopores. So the purpose of this research is we want to do two things. One is to consistently create hexagonally ordered nanopores in aluminum, and also observe the relationship between the pore diameter of said pores and the anodization voltage. So the first thing you're probably wondering is, what's anodization? So it's an electrochemical process where you are taking some aluminum sample and you're rapidly oxidizing it through putting some acid on the top and driving a current through it to increase the rate of oxidation. So what happens here is that you have a sample of aluminum, and by doing this anodization, you turn the aluminum substrate into aluminum oxide, creating this oxide layer here. And the cool thing about it is that you get these hexagonally ordered pores on the surface. That's the ideal situation you want to get out of it. So why do we use aluminum? Well, it's a soft metal, it's cheap, it's very easy to get in high purity, and it's easy to get samples from. So it makes it pretty ideal for making these kinds of samples. But it's not the only metal you can use. You can use something like possibly titanium. That's also used in other research that Dr. Shi does. So what you're seeing here is one of my samples. The outside edge over here being a hand-polished region of the aluminum, and the inside here is an electropolished region, which I'll talk about shortly. So what does the system look like? So up at the top left over here, we have the top layer of our cell where you can put oxalic acid or electropolishing solution for either electropolishing or anodizing. And the bottom over here is a metal portion where in this tiny square here you can put your sample. So you combine these two together, you can fill it with acid or electropolished solution, and it allows you to push a current through it using this circuit setup we have here. So we can measure what is the voltage we're putting through the circuit, we can measure what the current is going through it, and other things like that. So a cross-section of this sample here would be this here. So the bottom here is just your surface you put your the container on. This bottom part is the metal holder that we were shown before. This is our sample, a magnetic stir, your electrolyte or acid. And this right here is a platinum wire that you can put into your acid. Because if you put something like copper or anything like that, that's going to corrode inside of it. Platinum is going to blast through this process even if you're putting it in an acid. So then you push a current through here, and we can measure this by putting a resistor alongside it in a circuit. You can measure the voltage across it, and that can give us meaningful data when we're actually going through this process. So the first thing you want to do is you start with a sheet of aluminum, you hand polish it, which makes that kind of dull surface that you saw before. Then after that, you cut it into a small sample. We use about 2 by 2 centimeters, clean it in a bath, and then you can electropolish it after that. So the reason we want to do this is from first buffing it out with a mechanical polish, you get a lot of grit lines on it. So you push down a lot of the bumps to the surface, but you end up getting these scratches alongside of it. And we don't want that. We want it to have as smooth a surface as possible. So that's why we use an electropolish as well. That's going to create that mirror-like surface you saw in the center here, and it makes it much smoother. You get a lot less of these digs into the surface. So here's a cross-section of kind of what that looks like. You end up having some kind of bumps and ridges inside of here along with the general lay of the topography of it. What the electropolishing actually does is it reduces that grittiness. You still get the overall topography of the surface here, but it makes it much less bumpy. It's more smooth and ideal for making these pores that we want to create here. So after you electropolish it, the next step is to anodize it. So instead of using an electropolished solution, we use 0.3 molar oxalic acid, and we use voltages varying from 40 volts to 60 volts. So then, along with those parameters, we also care about how long the anodization lasts. So that can last anywhere from an initial small 10-minute window to possibly 12 to 15 hours overnight. So the range of time for anodizing it can vary greatly, and we use that the parameter of time to actually optimize this system. And along with that, there's another parameter we can talk about, and that's anodizing multiple times. So if you anodize it the first time, make an oxide layer at the top, making some of these pores, you can etch that oxide layer off from the top with a chromic and phosphoric acid mixture, and that allows you to anodize it again later, possibly doing anodization in multiple steps. So what do we expect when we take data from this? So initially you start, so this is going to be a graph of current density versus anodization time, but this current density is proportional to that voltage across the resistor I showed you before. So when you start, you are going to jump up in voltage, you're going to have pure aluminum at the top, and then as this oxide layer forms, it's going to become more resistant, so you're going to get less and less voltage across here, so you drop that current, Ohm's law. But then as these pores start to form, you get less resistance. It's going to build up more and more as these pores start to form deeper and deeper, and then as they get to a certain depth, it starts to plateau. So an example of that is in our actual data is we get something very similar to what we'd expect. You get an initial jump up of voltage as you close your circuit, decreasing down, rising back up, and then plateauing. So when you get data like this, this tells you, oh, the sample I've made seems pretty ideal. This is going to be a good thing to look at. So then, going on to actually confirm if what you actually got was good data, we're going to look at the sample actually in the scanning electron microscope over in the Keck Lab in Salazar Hall. So you can see over here is me working in the SEM to actually see some images taken in here. This is the scanning electron. And that allows that initial structure that was formed to dig down deep and actually form like solid pores that you can actually see. Versus the 10-minute anodization, you wouldn't be able to see them because they don't burrow in too deep. So then after that, you acid etch it off for about an hour. You do a final 20-minute anodization for any final pore formation, and then to see it under the scanning electron microscope, where you need a conductive surface, we acid etch that top layer off to be able to look at it. So then, this is what we actually end up seeing. So for a 40-volt sample, we see pretty small pores here that are pretty nicely distributed. And you can tell there's hexagonal ordering because if you focus on one pore there, you can see there's 6 of them hexagonally structured around. You can look around here. Pretty much no matter where you go, except for at these little deformities in the surface, that would take further optimization to get rid of. You can look at one pore, you can see there's a hexagonal structure to them. It looks pretty nice. So then if you take a look at the 60-volt sample, you have a similar ordering. If you look at one of the pores, there's going to be 6 of them around them, but the pores are much larger in comparison to the 40-volt. So we want to see, okay, they definitely look bigger, but how much bigger? So we can use image processing and the SEM to actually find the pore diameters for them. So these two charts here show 100 pores measured for each of the samples, both 40 and 60 volts. So on average here we had about 68 nanometers for the 40 volt with a pretty Gaussian curve, and then 112 here for a not as Gaussian but still pretty Gaussian curve for only about 100 data points. If you took more data points, you would expect it to get more normally distributed, and we get closer to an actual average here. So you can tell lower voltage, lower pore diameter, higher voltage, higher pore diameter. And then actually comparing those values, if you take the ratio of these two, 60 to 40 is about 1.5, the 112 to 68 is about 1.64. So those are pretty close when you're looking at those ratios. So that leads us to believe that there's probably some relationship between them, but we need to definitely find more data points here. Currently we only have these 2 data points. Further research would be into finding maybe at 30 volts, 70, between 50, ranging around there, seeing if there's that linear dependence that we'd expect to see when you increase anodization voltage diameter. So now we have some very nicely ordered pores, and we can see them under the SEM. So what's the point of doing this? Well, first off, anodization, it makes a very durable and corrosion-resistant finish. So that surface we have there it's long-lasting. We don't have to worry about any aluminum wearing over time because we already made that oxide layer. And then actual applications for this is one of them, we can fill these tiny nanopores with a metal, and by filling those, we make little nanowires. And those are very important because with standard classical wires, you have things like Ohm's law, V equals IR, all the normal physics you learn, like that's what she said, like in physics do, electromagnetism. But those tend to change when you go to the nanoscale. There's different physics governing how things behave for such small diameters, and to actually be able to test those models that have been formed, you need to actually have these nanowires, and this is one of the ways to construct these nanowires. Along with that, instead of filling them with just any metal you want to fill them with, you can fill these with a magnetic material. And if you're able to get rid of those little deformities that you saw here, these white bumps that you see in both of them, you can get rid of those, making it as smooth as possible, less deformities. You can make it as ideal as you want, and then by filling them with a magnetic material, you have a data storage structure. If you fill it with a magnetic material, you can have magnetic field up being a 1, down being a 0, and then you have a large amount of data storage in a very small area, considering how small these pores are. So, as a final discussion here, we were able to find that lower voltage anodization leads to smaller pore diameters, and we found the optimal parameters for making these hexagonally ordered nanopores. So further research would be into finding further optimization for the system to maybe get rid of those small bumps, make sure that everything is hexagonally ordered as possible, and that the pores are as close in diameter as possible, that they have similar diameters to each other, that Gaussian distribution being a little bit sharper. And I'd like to thank Dr. Shi and Steve Anderson for all their help in this project.
Yes. Can I get you to explain a little bit more about the oxidation process? I think you had an image on it.
So what kind of image were you thinking?
It was one with the electrolyte.
Yeah. So the idea is we want to cause oxidation to occur on the surface of the aluminum rapidly. So that normally happens like for maybe like iron rusting. There's oxygen in the air, it naturally forms that rust layer. We're trying to create that to happen on the surface of the aluminum, but much more rapidly. So what we can do is fill this with oxalic acid. There's oxygen readily available. And by pushing a current through it, it causes that reaction to occur much faster, which allows that oxide layer to form and burrow in deeply.
So is the aluminum in contact with the electrolyte?
Yeah, so right here, it's kind of hard to see because I didn't make enough space, but this would just be a magnetic stir that's spinning it, making sure that it's as evenly distributed on the surface of it as possible, and it allows it to create that oxide layer on the top.
Yes.
Could you further explain the role that this sort of thing plays in information storage and whatnot?
Let me go forward. Okay, so imagine that each of these things is filled with a magnetic material. If you were to change the magnetic field in it, up could be 1, down could be 0. If this was as ideal as possible, like that first slide showed, you'd be able to actually determine where exactly this position on like a grid would be. You could go and measure that, see if it's 1 or 0. That's your binary bits. And you can use this as a way to just store data. The same way you'd store data on a normal magnetic-based hard drive, you can use it similarly for this kind of data storage.
Did you get your initial voltages and procedures from industrial anodization?
Yeah, it was based on other literature that Dr. Shi showed me. They used some, most of the time it was about 60 volts, which is why we decided to be in this range. But then actually saying how that compared with other, like if you lower the voltage, how does the sample change? So we wanted to stay in the ballpark of what other people had done before, but we wanted to change it depending on the parameters that we needed for our system.
Any other questions? Yes.
Why is the pore size data skewed right on your 60-volt histogram? I'm wondering as to why that is not as normal as the 40.
Yeah, so I would, well actually you can kind of see it in this picture here. If you look at like one of these dots, you can see some of them, like this one's ended up being a little bit smaller. With the smaller voltage, we ended up having a much more uniform size for them. That's why.
Are they bumping into each other on the 60? If
Yeah.
they're bumping it, if there's an upper limit to what it can reach, it'll automatically be skewed.
Yeah, and that's why if you have a lower voltage, it's not burrowing as much, you're going to have that more of a boundary to it. So it won't be as
There's a
skewed.
boundary.
Yeah. Thank you, Dr. Johnson.
Okay, all right, let's thank Adam again.